So let's continue. Let's look at the possible implementation approaches that are available for digital design. So the first is custom design. And by custom design, we essentially mean that there's a transistor by transistor design of the complete circuit. Okay. And then we will go after every single aspect in detail. So transistor by transistor design of the complete circuit. Then we have what is called semi-custom design. So with semi-custom design, we mean that we are using something that has already been pre-designed. Okay, and in the case of semi-custom design, we have essentially two options. One is to do a cell-based design, which means that we have some cells, some particular blocks that have been already designed, and we can just use them. But in any case, we need a complete manufacturing run to fabricate the integrated circuits. Okay? So there are some blocks that have been already designed, but everything has to be manufactured again. In the case of cell-based design, we typically have two different options. One is the so-called standard cells, which means that very simple basic cells have been already designed and are available to be placed. For example, single logic gates. Okay. There is another option for cell-based design in which we have some macro cells, which are larger cells. For example, a memory block, a large memory block already ready to be used, already designed, ready to be used and placed on silicon. These are two, let's say, extremes. There are lots of intermediate solutions. Then, still considering semi-custom design, we have the options so-called array-based design. The main characteristics of array-based design is that we do not need a complete manufacturing run. Some part of the manufacturing has been already done, so we start from let's say, a half-done chip, or we start from a completely fabricated chip, and the only option we have available is to program it. Okay, so one of the options is the so-called gate array. So in the gate array, some parts of some cells and some important building blocks have been already partially fabricated. Basically, it means that we only need to put the interconnections and eventually to program it, and possibly to program it. Okay? And then, on the other hand, we have the so-called reconfigurable logic, such as, for example, the FPGA, or the, let's say, in the more extreme case, the microprocessor, in which we already start with a chip that is completely done and fabricated, and the only option that we have is to program the hardware. So, again, we have the complete set of options that goes from custom design to standard cells, macro cells, gate array, and reconfigurable logic. In this order, you of course have an increase of flexibility, as I mentioned before, and typically a decrease in performance. So the trade-off is this way. On this side we have higher performance, and on that side we have higher flexibility. On this side we had higher non-recurring expenses, because everything has to be done. So if we use, for example, the custom design, not only we have to manufacture completely the chip, but we also have to design every single part of the chip. Of course, we design less and less here, less and less here, and in those other situations we have less non-recurring costs, because also the masks have already been done, so we can save something from the non-recurring fabrication costs. Of course, for many different reasons, also for commercial reasons, we have higher recurring costs, in the sense that when you buy an FPGA, for example, you buy it for a much larger price than the cost of silicon if you had to do it yourself. And of course, it really depends on the application, because if you really need an application for, let's say, 100 different chips, you don't go this way. If you just need 100 pieces, you prefer to pay for a high-performing FPGA, for example, even if you have high recurring expenses, but in the end you can save a lot to the non-recurring expenses that are very high if you have a smaller number of chips. Okay? If you, on the other hand, have a large production, 100 million pieces, for example, then for 100 million pieces, the non-recurring costs are not important for you. You can prefer to go for high performance and then do everything from scratch. So, okay, let's examine in detail these blocks. Because in addition to the considerations that we have done, there are also other considerations. So we already said typically you do custom design with the advantage that you have high performance, of course lower flexibility, and it is obvious that it is more time consuming. Okay, the fact that it is more time consuming has actually two consequences. One is the high cost of design, and we have already discussed that. It means that you have high non-recurring expenses. Okay, that is clear, we have already discussed. There's an additional issue, which is actually extremely important, is that you typically have a high time to market. Because it's very hard that you have a very, because in principle, even if you have a large size of the design team, you end up with a few months, 1-2 years of design time in order to perform a complete custom design of a complex chip. Okay? And this, from the point of view of, let's say, market opportunities, can be a problem. You typically have a small window of time in which your product is actually very competitive, and of course, the high time to market is an additional problem. It's not just a matter of cost, there's an additional problem of high time to market, because you can lose the good timing and therefore can enter the market at a time in which your solution is not the only one anymore, so you have to decrease the price in order to sell. So there are a few typical cases in which custom design is used, and actually are the ones that are shown here. Of course, you always use custom design for the blocks that have to be used many times. The standard cells that I mentioned before, they have to be designed at least once the first time. And of course, the design of the standard cell is a sort of custom design. And in that case, it is extremely useful to do a custom design, because of course, especially the blocks for the standard cells are going to be used several several times, okay, very high number of times. So in that case, I mean, the non-recurring costs are not really an issue. The other things that are custom designed are typically very high volume ICs, such as, for example, microprocessors. I must say that not all parts of the microprocessors are custom designs, but there are parts of the microprocessors, especially for the high volume ICs, that are custom designed. And also, you typically perform custom design when cost is not an issue. For example, for defense applications, for supercomputing applications, traditionally all the supercomputers of the 80s and of the 90s had chips that were completely custom designed. Of course, in this case, cost is not an issue, and you want custom design because you have high performance. So these are the typical situations in which custom design is doable and is done. Now, let's look at the different types of semi-custom design. Cell-based semi-custom design. So, as I mentioned, in the case of cell-based semi-custom design, we need a library of cells, of standard cells or of macro cells that we can use. The standard cells are very, let's say, typical blocks. The blocks that are used really millions or billions of times. All the logic gates, 2, 3, 4, 5, 6 inputs. All the so-called medium scale of integration circuits. So the decoders, the multiplexers, the encoders that are used several times. And that's it. You have a library of standard cells, and you can pick the type of logic gate or circuit that you need, and you put it in your design. And the macro cells I already mentioned, they can be typically memory banks. There is also another, let's say, special case of macro cells that are the mega cells, which are, let's say, macro cells particularly large. And especially in recent years, as a mega cell, you can have a complete microprocessor that has been already designed, and you really just need to put the microprocessor in your chip. That is already done. Or some specific input-output interface. For example, the PCI interface typically is a special macro cell that is already done. Since it's used almost in every digital chip, you pick it and you use it. Okay. How do you use the standard cells and the macro cells? The typical situation is the following. This is let's say, a pretty old image of a first generation of standard cells. So this is let me show you. This is the die. This is the piece of silicon in which you have the circuit. These are the pads for the input and output wires. And this is the area in which you have the silicon chip. Actually, in the case of standard cells, the typical situation was that you have rows in which you can put the cells. And the cells were designed in order to have all the same height and different width depending on the complexity. So just as in the case of Lego, as with the Lego building blocks, you know what type of block you need, and in a row you put in the order which is most convenient for you the different standard cells. Okay, then you have let's say some space, and then you have another row, and so on. So you have many different rows, and the space between the rows forms the routing channel that is used for the interconnections between the different building blocks. So each standard cell is done in a way of is done in such a way as to have the input and output input and output voltages on the lower or upper sides, so that it's easy to use the routing channel for the interconnections. Okay, so that's it. Displacement of the various standard cells on the rows can be done automatically, or can be done manually, or can be done in a mixed way according to the complexity of the circuit. So, of course, you see that in the end this solution is not extremely efficient, because you do not have very dense cells. You use a lot of space for the routing channels. You see there's a lot of white here, and so the white in this image is space that is not used for interconnections or for logic. Okay, so this is a very a relatively old type of standard cells. For the newest ones, one has a much more compact solution, because basically you do not have a routing channel. Typically the routing is done on top of the standard cells. So the routing is not limited to the periphery of the cells. You can just connect a point in the middle of a standard cell with another point in the middle on a second standard cell, so all the rows are adjacent to one another. Everything is much more packed, and this is the image that you see here. Typically these violet lines, so I don't know exactly where they are in this particular image, but they are used for in this case for the ground and the power supply that have, so because it's a type of signal that has to be sent to all the blocks. So the ground and power supply, clock possibly, and so on. The reason why this can be done only recently is that, let's say, for the first CMOS technologies, you only had 2 or 3 layers of metal. And for the new CMOS technology, you have up to 11 layers of metal. So you can use a few layers of metal for the interconnections in the cell, and then you can use the upper layer for the interconnections between the cell and they're on top of the cells. So this is a situation. You can see that if you look at the image, it is more regular than let's say a completely custom CMOS structure, but of course less regular than an array of identical modules. So, how do we arrive at a standard cell implementation? Because of course, before you know exactly what are the blocks that you need to design the complete chip. And the typical sequence of design step that has to be done is therefore the following. We start with a design at a high level of abstraction, typically using a hardware description language. And this part of this description in terms of hardware description language is something that, of course, is discussed by by Professor Fanucci in the class. Then once you have the hardware description language, you can use some specific logic synthesis tools in order to translate this description in terms of a high level language into a gate level design. So one typically describes the operation of the integrated circuits at a high level of abstraction. Of course, you see that there are behavioral descriptions or more analytical descriptions of the behavior of the circuit. But in the end, after the use of this logic synthesis tool, you arrive to a gate level design. A gate level design is a design of a logical circuit at the level of single gates. And when you are at the level of single gates, then you can start to use a standard cell approach in order to design the complete chip. Once you have a gate level design, then you can use so-called placement and routing tools in order to place all the standard cells corresponding to each gate you need onto the silicon die, and also start to place the routing, the interconnections between the gates, the interconnections between the output of one gate and the input of the following gates. So at this, you need to reach this level of description in order to think in terms of standard cells, and then this is almost, this part can be almost automatic. The placement and routing tools, depending on the complexity of the chip, can already place all the standard cells and put the routing, and then one typically has to adjust the routing and adjust the position of the standard cells in order to, let's say, improve the operation of the whole chip. So standard cell layout, and then once the standard cell layout is complete, one can go to a foundry, because at the end of the design in terms of standard cells, one is ready to obtain the different masks for the various levels of let's say, doping and the different dopings and regions of silicon, and directly go to the foundry. Okay, this is the typical process. You can also observe that this type of process is very convenient for a fabless operation, because from here to here, basically, you don't need to interact with the foundry. You only need to know the constraints that the fabrication process is giving you, which are described in terms of design rules. And then only at the end you can go to the foundry. So this type of, let's say, scheme is very suitable for the fabless industry model. We already discussed it. In the fabless industry model, you have two sets of actors. The fabless companies that typically only do the design, the testing of the chips, and the sale. And you have foundries that do the fabrication. Okay? Just to be, we mentioned a few of the companies, of the, let's say, international companies in this scheme. I would say that at the moment, the most important fabless company is Qualcomm. And then you have several foundries. Most of the foundries are located in Southeast. Here are the three most important ones. TSMC is in Taiwan, UMC is in Taiwan, and SMIC is in China. Okay, so there's also a difference in terms of geographical, let's say, position. If we consider what we have discussed up to now, typically the standard cells are provided by the foundry. So the custom design of the standard cells that are used for a standard cell design is done by the foundry. And this is, let's say, a significant advantage, because when a fabless company designs a chip using the standard cells provided by the foundry, it is completely sure that these standard cells will work, okay, because they are perfectly, let's say, adapted to the fabrication process of the foundry. So this type of custom design is done by the foundry. Actually, what is happening in the recent years is that the foundries also do some macro cells, not only standard cells, but also macro cells and more complex cells. Okay. Again, to be complete, we already mentioned this other type of semiconductor industry actor, the IDM. IDM means integrated device manufacturer, and typically is a company that does both the design, the testing and the sale, and the fabrication. So they integrate the activity of a fabless company and the activity of a foundry. Okay? And now very few IDM are still in operation, especially for the most advanced CMOS technology circuits. I would say the most important ones are Intel and Samsung. Then actually there are other actors, but they are not actually performing fabrication at the highest level of scaling. For example, STM, which has a huge presence in Italy also, is Franco-Italian as a company, actually is an IDM, but not for the most advanced technology nodes. Oh, with respect to this scheme, I would say that among the biggest fabless companies, one should add also Apple here, because as we have already discussed in the latest versions of the iPhone and various tablets, many of the chips have been completely designed by Apple and fabricated by other companies. So it's the situation is moving now. Oh, finally, there is this other type of actor which is important and let's say can be understood once we know what is cell-based design, is the so-called IP vendor. So an IP vendor basically sells a macro cell library, specific macro cell libraries to be used in this type of cell-based semiconductor designs. Can be a macro cell or more recently a mega cell. In this design flow, there are two options in which one can sell a macro cell. At this level, in the standard cell layout, one can just sell the layout of the complete macro cell, or at the level of gate level design, one can sell a macro cell and then let the fabless company do the placement and routing. Okay. Also, this type of let's say business model, type of actor in the semiconductor industry is pretty recent, and I would say that the most important one is ARM. ARM, you know, is a microprocessor company. They do not fabricate the integrated circuits. Actually, they do not design the complete chips. They only sell the macro cell module of their microprocessors. Okay, you can buy from ARM a gate level design of a microprocessor, and you put it in your circuits and do the placement and the routing of all the gates. And the other possibility is that you buy the macro cell of a microprocessor for some specific technologies already completely designed. So with already the layout done. Okay. So as I mentioned, ARM is probably the most important IP vendor. There are also other IP vendors that, for example, sell specific input-output interfaces. That is quite common. Or specific memory modules. That is also quite common. It's becoming, let's say, quite common as a type of actor in the semiconductor industry because, of course, it requires almost no capital expenditure. You don't need to fabricate anything. You actually don't need to do let's say a design on silicon. You typically can also only do a gate level design of the chip. Okay, this is something that I already mentioned. I forgot that I had a table for that. I mentioned before that you have two types of macro cells. You can sell basically the gate netlist, the design at the level of a single cell, and in this case we say that you sell a soft macro cells. But you can sell also a custom designed cell for a specific CMOS process. So you say you already have all the gates laid out on silicon. And in this case, we say that you're selling a hard macro cells. There are differences, and the difference is typical, is the same trade-off that we have already observed. Because in the case of a hard macro cell, it's designed for a specific CMOS process. So it means that you cannot change, it is optimized for that specific CMOS process. So the performance for that specific CMOS process is better than what you can have with the soft macro cells. But of course, if you want to change after 2 years the CMOS process that you want to use, the macro cell that you have is not good anymore. You need to buy a new hard macro cells. Instead, with a soft macro cell, you can port it to a different CMOS process because you have a gate netlist and then you can perform the placement and routing again. Okay, so in the first case, you have better optimization but less flexibility. In the second case, you have less optimization, but of course, good portability, good flexibility in terms of portability in this particular case. There are these two different options. Okay. Just as an example of macro modules, you can have, for example, an SRAM. This is an SRAM block of 8K bit. Right, you can recognize the modularity. Of course, a memory block is extremely regular. You just have some control part here, and then all the rest is the array of memory cells. And then in the case of soft macro modules, basically you have a piece of code and then you have to design to do yourself the placement and routing. These are just illustrations. They do not add anything to what we have already said. Okay, let's have a look of the let's have a look to the semi-custom design flow. Basically, it is identical to what we have already described, but with some more details and also with some let's say, illustrations of the iteration that we need to do. So let's look at the different phases. We can distinguish two parts, two let's say, main phases. A phase of functional implementation and a phase of physical implementation. Okay, so at the level of functional implementation, you want to check that the circuit works. So the circuit means the sequence of logic gates and their interconnections works in the sense that it performs the functions that you need. And then in the physical implementations, you want to arrive at the physical layout of the chip in order to send everything to the foundry. Okay? So there are two different steps, two different phases. For the first phase, we already mentioned the main 3 points, but it's interesting to see let's say, the loop that is required. So we first have a design capture phase in which basically use VHDL, to the hardware description language, and the IP blocks that we already want to use. For example, we can decide to use let's say, a microprocessor, an IP block for a microprocessor or for a specific input-output interface. Then we verify the functionality of this description with a hardware description language, typically. Once we are ready at this phase, we can perform a logic synthesis. And this is done with a logic synthesis tool, typically, at the end of which we have a list of all the gates, the so-called gate netlist, and then we have all the constraints in terms of placement and routing. These constraints, we know what are the interconnections between the different gates, but also the logic synthesis phase gives us some constraints on the interconnections. For example, the length of the wire between two different gates, because the delay in the propagation of the signal between two logic gates is a function of the length of the interconnections. So we typically have a constraints in terms of maximum length of the interconnections, and we have to use this constraint when we place the two different gates on the silicon die. Okay, this is generated by this list of constraints is generated by the logic synthesis tool. So have the gate netlist, the list of constraints. At the end of this phase, we do a so-called pre-layout simulation and verification. So this means before doing the layout, when we have only the gate netlist, we perform a simulation at the level of gate netlist in order to verify that the behavior is the same of the hardware description language based description of the circuit. So we need to check that at the gate level the circuit is behaving exactly as we want. And this verification is done by performing a series of checks. For example, by providing some inputs to the circuits and verifying the behavior, the output of the circuits with the two different types of description. Of course, if the control check answer is no, we have to repeat this cycle again, because something has gone wrong. Probably the logic synthesis has not worked as we wanted, we need to understand why, and so on. If the check works, then we can just go to the physical implementation. So we need to pass from the gate netlist to the physical layout of the chip. So the physical layout of the chip is done in a series of steps. Again, let's discuss these steps in detail. The first step is called floor planning, which means let's place every gate in its particular position. For example, in the case of a standard cell implementation, we need to place every gate of the netlist in a position on a row. Okay? This is the floor planning. We more or less have an idea of the total space that is required by the chip. So the main reason for doing the floor planning is understanding the total space. The exact position of the pieces is, let's say, at this stage less important because we need to adjust it in any case. Then we need to do the second step, which is the placement and the routing. So with the placement, we decide the exact position of each gate on the basis of the constraints that are given by this step. And we also, on the basis of the same constraints, perform the routing. This typical step is done, as I mentioned, quasi-automatically, in the sense that there are some software tools that do it, but then one typically needs to perform some adjustments because the constraints are not satisfied. But the nice thing is that once you have the placement and routing done, then you check the constraints via software, you see the constraints that are not satisfied, and then you work specifically only on the constraints. So the advantage of using the tools is that you can work on the exceptions. Most of the thing is done automatically, and then you work manually on what is not working automatically. Okay. At the end of this process, one only needs to perform a verification. So, in order to perform a verification, one needs to do the following thing. At the end of the placement and routing, you already have a physical layout of everything. Okay? You have a physical layout on the circuit on silicon, and then you need to check if this physical layout corresponds to the gate netlist that you have here. And you have already verified that the gate netlist corresponds in terms of behavior to the initial design. Okay? So, how do you do the last step? There are tools that perform an electrical circuit extraction. Then, from the layout, without knowing anything about the circuit, they extract an equivalent circuit, an equivalent electrical circuit that you have here, and then you simulate the extracted circuit and verify that it works as the gate netlist before. So it responds to the same inputs with the same outputs. Okay? If the answer is yes, basically you can say that the physical layout is identical to the gate netlist and behaves as the initial design. And so you can go to a foundry. So from this physical layout, the masks will be generated and the integrated circuits will be fabricated. If the answer is no, you need to go back and then to do the placement and routing again and verify what's not working. Okay. This type of procedures ensures that the physical layout is consistent with what you want from the circuit. So, of course, probably I need to mention why this is extremely important. This is extremely important because it's the last step, send to foundry, is extremely expensive. Okay. And then when you go to a foundry, you want to be sure that the chip will work. Okay? You cannot simply, of course, this is not the last step is not software. You cannot simply do it and then check the bugs. It's too late. The hardware must perform as expected. Okay. You need to know that even for a small chip, if you want to do a set of masks is going to cost a few $million. This is the size, a few $million. So you only do it if you're pretty sure that it's going to work. Otherwise, you prefer to, let's say, work a bit on software in order to be sure that everything is working. Okay, this is for the semi-custom design flow, the cell-based and the macro cell-based. For the array-based implementation, the thing is different because we do not require a complete manufacturing run, and therefore the situation is a bit different. Okay, as I mentioned, there are two different options. Let's look at the two different options that we have. First, we have the first option is the gate array. In this case, essentially, we have mask programmable arrays. As I mentioned before, some parts of the fabrication have been already done, and we only need to do the interconnections. So the diffusions of the various areas have been already done. We only need the metal lines. So, of course, this is doable for only, let's say, for only a subset of the conditions, but typically let's say most combinatorial logic and many finite state machines can be performed with a gate array. Okay. Of course, this means that the non-recurring costs are lower because you only have as non-recurring costs some part of the design, which is fast because you typically have only to design the interconnections, and from the fabrication point of view, you only have to pay for the fabrication of the metal lines. So basically, you need to spend money for the masks of only the metal lines and not the other masks, which is much less expensive. Then the other possibility is, for example, the use of field programmable arrays. In this case, you only you only need to program the hardware. There's a complete separation between the manufacturing phase and the implementation phase. The chips have been already fabricated. You just buy them and you program them. Okay. Of course, in this case, the time to market is the shortest you can actually have. You have a very small time to market and very low non-recurring expenses because you don't need to fabricate everything. You need just to buy the cell, to program it, to buy the FPGA, and to program it. So the only expense you have is the coding expenses, and then you have the recurring expenses, which are typically high because you pay a lot for every field programmable array. I mean, the profit is made by the company which sells the FPGA. sometimes you also, this is also cost, you have a performance loss, because of course the circuit is not optimized for your specific function, and you typically compensate this performing loss by buying a more expensive FPGA which has a best performance, intrinsic performance. So typically everything is translating into high recurring expenses. So this is typically used in two cases. First, when you have very low volumes. So if you need to make something in 100 pieces, so the volume is extremely low, and then it's good to go to the FPGA phase. And the other case is when you need to do some fast prototyping of a chip. So you can do the first prototype, first generation. It's almost a pilot production with an FPGA. If everything works, then you substitute if everything works and then you want to go to large volumes, you substitute the FPGA with a semi-custom chip, because in this case at least you have lower costs per item. Okay, regarding the FPGA, that one type of thing that we need to mention is how we program the hardware, because there are different options actually. There are Fusebased FPGA, non-volatile FPGA, and SRAM-based FPGA. So, what do I mean by that? You should consider that we need to program a piece of hardware. So how do you program a piece of hardware? You need to actually, let's say, decide by software if an interconnection is present or it is not present between two logic gates, for example. And in the case of Fuse-based FPGA, we have the following situation. Typically, you have that the interconnections are already placed between all the logic gates in a generic block, and then you can open the interconnection. For example, let's say one typical situation is a fuse-based programming. Typically have an interconnection like this, in which you have a conductor, a metal wire, with a narrower region, and this behaves like a fuse. In order to program it, you push a high current through the wire, and you have a high power dissipation in the narrow region. This region essentially blows up, and then the interconnection is interrupted. The interconnection is interrupted. So it's like a fuse, what we call in Italian a fusibile. Okay, that's it. There are many FPGA that are sold in this way. This means that from the design point of view of the FPGA, you need to put a lot of interconnections, and then during the program operation, one needs to open all the interconnections that one does not want. Okay? You need to consider that this is typically done automatically by a specific software. You decide what's the interconnection, what's the gate level design of the chip that you want, and then the software understands how to map the gate level description of the circuit onto the FPGA by interrupting a few interconnections. Okay? Of course, this is a write once solution. When the fuse is open, you cannot change mind. Okay? There is also the, let's say, complementary solution. It typically depends on the company and on the type of chip, in which you have an anti-fuse solution, which means that typically you have a circuit that is open, and that with a high voltage you can close. This is the example. You have, this is just a picture. You have two lines, this one and this one, that are separated by a thin dielectric. So at the beginning, they are completely insulated, so there's no conduction between the two regions. And then during the program phase, you can apply a high voltage between this line, between this line and the other line. With this high voltage, you break the silicon, you break the insulator, and then you put the two lines in contact. So this is an anti-fuse. You did not have a contact, and then you cause a contact between the two lines. And again, also in this case, you have a write once solution. Once you do it, you cannot change. And in the typical situation, you have something like this, a sort of seen from the top. You have a few lines in this direction, a few lines in this other direction, and then you decide, they typically have no contact, and then you decide when you want to have actually contact by this initial programming phase. Okay? So this is, and this is also quite common now. For example, most of the Atmel FPGA work with a fuse or an anti-fuse solution. It really depends on the company. Okay, another option that you can have is the non-volatile FPGA, in which typically you have a non-volatile memory which decides if the interconnection is present or is not present. So you have to program a bit of memory, a non-volatile, a sort of flash memory, a non-volatile memory, and that bit allows you to put into contact two lines, two conductors, or to keep them isolated. Okay. The advantage of using a non-volatile FPGA is that you can change the program. Okay, you can write a 1 or a 0 in the position of the non-volatile memories, and then therefore you can program the contact, or let's say eliminate the contact. And the second option is similar to the previous one, but instead of having a non-volatile bit of memory, you have an SRAM-based FPGA. So in the case of an SRAM-based FPGA, typically what you do is the following. If you want to perform a combinatorial function, you know that any combinatorial function can be performed by a lookup table. Okay? And actually, this SRAM is the lookup table. So this type of FPGA works in this way. At turn on, during the boot, there's a boot phase during which the FPGA reads an external memory on an external ROM, on which all the content of the lookup table is written. Then all the content of the lookup table is written, is, let's say, transferred on the internal SRAMs, and so you program all the combinatorial logic. Typically, you have different blocks depending on type of number of inputs, number of outputs of the combinatorial logic that you want. Of course, the advantage of using an SRAM-based FPGA is that, let's say, the reprogramming of the FPGA is extremely easy. You just need to change typically, it's exactly like changing some code. You don't do anything different. You change some code during the compiling phase. Actually, the code is written in the ROM, and therefore you turn on the FPGA and it reads all the ROM. Of course, there is some difference among these three different situations. You can typically obtain a higher performance with a Fuse-based FPGA. Again, the situation is always the same. The more you move to software, to a larger component of software, the less you have in performance. Just to understand what type of logic can be programmed, take this just as an example. If you have some array-based programmable logic, such as, for example, a PLA and a PAL, a programmable logic array or programmable array logic, those of you that have done the basic course in electronics have already seen that, know that for any combinatorial logic function, you can use an array-based programmable logic, and you can program either the AND array or the OR array, actually, or both. And typically, the program happens by having this contact or not having this contact, each of those. So basically, this is perfect for some programmable logic. You can program every single contact here. You can start with a situation in which you have all the contacts there and you remove the ones that you do not want. Again, I'm speaking as if one did this, let's say, manually, but in practice you simply let's say, describe in a software tool what is the function that you want, and then the software automatically knows what contact must be removed. Yeah, this is something that we already discussed. Okay. Okay, this is just a set of pictures to let you understand what's the view of what happens here. This is a photo of a chip realized with a sea of gates. You see this is the structure. Basically, you only see the interconnections, these red lines here, and they are pretty random because you have some random logic, and the interconnections are, let's say, put by hand or automatically, but on some logic that is not modularized. Instead, in this case, you have a memory subsystem, so a type of logic that is very regular, have several memory blocks, and therefore let's say the design is extremely regular in this case. So consider that all the diffusion levels are repeated. We are only changing the top metal lines for the interconnections. On the other hand, if you look at an FPGA, it is extremely modular. You see, this is every small block consists of some logic and an SRAM on which the different lookup tables are written. these blocks are all connected by some lines that bring the power supply, the ground, the clock, and so on. And so typically an FPGA is extremely regular. The differences between the functions of the different blocks are written into the memory, so they cannot be seen by an image. In the previous case, let's say the functions are encoded in the interconnections, and of course you see the difference by looking at the picture.